Hey AP Calculus BC students, Mr. Record here. We're going to take a look here at an interesting side component to the concept of the alternating series. Hopefully you've sort of have been briefly introduced to the alternating series and have been exposed to the alternating series test prior to watching this video. Because this goes into just a little bit more detail and kind of gets into the idea of the second aspect of the alternating series, which is determining different types of convergences, absolute convergence versus conditional convergence. So I have videos where I've already discussed the actual alternating series test that's outlined here. You can find those on my YouTube channel. And with that, I actually did this example 1, part A, and a part B. And then we talked about the alternating series remainder, which is not important necessarily in the purpose of this video, but in a typical calculus book, these would have been discussed prior to the introduction here of absolute and conditional convergence. So that's the topic of this particular video. And I'm going to start off by sort of taking you down memory lane here just a little bit and perhaps reminding you of a particular theorem that we had discussed a few sections ago, at least in my class. And that was the theorem that says that if the series where you take the absolute value of the nth term expression and you sum it up and you know that it converges, well, then it just so happens then really the absence of the absolute value really won't affect the outcome. And really what you're looking at here in this particular instance is if I were to compare the two. Obviously by taking the absolute value we've made all terms positive. So maybe we have a series that does something like this, and I guess it looks as if my convergence is going to be to 0 perhaps. In this particular case. And then if we look at, say, another series that perhaps might bounce around a little bit, like this, and have some positive terms and some negative terms, well, if I know that by adding these farther out terms here with the absolute value pretty much gives me sums that are negligible, and thus allows my whole series to approach some kind of a convergent value, then I'm going to really encounter the same thing even if I had not taken the absolute values. So that's one of the things that is going to be a pretty prevalent concept here. And then I've got the definition here of absolute and conditional convergence. And prior to that, you look up here and you see, hey, this is somewhat of a familiar series. I talked about it in a previous video. This guy is actually called the alternating harmonic series. It was my example 1, part A, and we had discovered that the alternating harmonic series is actually convergent. If you apply the alternating series test, in no time at all, you will have found out that this is convergent. But alas, we remember that the harmonic series, that would be just the series as n goes from 1 to infinity of 1 over n, that guy is divergent. So hold on a second. This particular series with this alternating component converges. But yet take away the alternating component and you have a series that diverges. Well, that is exactly what conditional convergence is all about. So you can see down here in my case 2 that if the absence of the absolute value causes the series to diverge, which is exactly what happened right up here, by taking away any potential -1 to the n or -1 to the n plus 1 term, thus allowing for negative terms to pop up every other time, I end up with a divergent result. But if I were to leave the negative component in then I find out that I've got a convergent situation. That's absolutely convergent. Now, to be the best kind of convergence, or absolute convergence, then that just means that you're basically going to apply, if I can go back up, theorem 9.16. And that's what case 1 is about. Put the absolute values around the original expression. If you know that's going to cause the series to converge, then that means that the original nth term expression with its summation is going to do the same thing. I know it seems a little confusing, but when you practice it, look at several different kinds of examples, you'll start to feel a little bit better about it. So if we take a look here at our first example, determine whether this series is convergent or divergent. Classify any convergent series as being absolute or conditional. Well, what we're going to see here is a very interesting series that involves some exponential and some absolute value. And our first job is just to flat out determine, well, what's going on with, say, this particular series. Let's take the absolute value of our nth term expression and see where this takes us. Well, whenever you take the absolute value of what is ultimately an alternating series, it essentially eradicates this alternating component. That's what I like to call that, -1 to the n or -1 to the n plus 1. I like to call that the alternating component. So that leaves you with n factorial over 2 raised to the n, and it becomes our job to figure out what is he doing. Now there's a variety of ways that you can do this. One of the first tests that we learned was the nth term test for divergence, is where you analyze, well, what would the limits be as n approaches infinity of n factorial over 2 to the n. And as long as you do not get 0, then you can assume that this series will diverge. Now, obviously, you can't really do some calculations with this. You can't just plug infinity in for n, because you do get an indeterminate form, infinity over infinity. But before you start to get real excited about, hey, let's use L'Hopital's rule, L'Hopital's rule just doesn't play real nicely, or derivatives in general don't play very nicely with factorials. So in my classes, we had talked about a few weeks ago that anytime that you have a factorial in one part of your fraction, whether it's the top or the bottom, versus pretty much anything else, an algebraic component like an n or an n squared or an n cubed, or even an exponential component here like a 2 to the n, or even a 3 to the n, or 4 to the n, which piece is going to grow faster? Well, it turns out the factorial will win every time. And it probably will take, I'm guessing, about, let's see, maybe a 4 factorial to get us convinced of that. Up until n being 4, I think the bottom is going to be bigger, right? Think about 3 factorial up here making this 6, and 2 to the third making this bottom 8. But by the time you let n equal 4, the top definitely takes over. And as n goes from 4 to 5 to 6 to 7, we're going to find out that without any doubt, this guy here is going to become infinity. All right? Since infinity is not 0, that means the nth term test applies, and this diverges. So we've established that. What does that mean? Well, if we were to back up and look at this really messy page now, I'm going to clean up some of this here. It says that if the summation of the absolute value of our nth term diverges, then there's a chance that we may be looking at conditional convergence. But that's only if the original problem converges. Well, what is the original problem doing here? Well, you can go ahead and apply the alternating series test on this. I'm going to abbreviate that. And you might ask, well, what exactly is the alternating series test? Well, remember, it's got two criteria with it. The first criteria of the alternating series test simply says that if you were to find the limit, as n approaches infinity, of the non-alternating component, well, that would be the n factorial over 2 to the n. Well, of course we can find that limit. We already did that up here for the nth term test, and we know that the answer is infinity. Well, if you get a result like this, you can stop with the alternating series test, because what you're looking for with the alternating series test, and I'm going to go ahead and I'm going to go back several slides here to when I first introduced the alternating series test. Right? Again, what we were doing is we were looking at a series that sort of resembled this guy, and we just took the limit of the AN piece. That would be the piece without the absolute value. Well, in order for us to even remotely say that we are going to converge, the answer to that limit had to be 0. And obviously the answer to our limit was not 0. We got infinity. Whoops, sorry about that. So we can then say the alternating series test says that we diverge. Well, if you're going to diverge in both cases, then there's no question about the final answer to this. This alternating series diverges. Right? There's no such thing as conditionally diverge or absolutely diverge. There's only absolute diverge. Diverge is absolute diverge. Okay? You only categorize when you have conditional. Okay? Now again, the only way that we could have been any type of convergence here is if this guy here perhaps would have said converge. Okay, we're going to read these one last time here. Okay, read these one last time. If the summation of the absolute value diverges, but the original alternating series converge by using the alternating series test, that's when you've got a conditional. But if the absolute value converges, then game over. You can say by theorem 9.16 the original summation is going to absolutely converge. Let's take a look at one more example. Maybe this will get you feeling a little bit better. This is part B of example 3. Now, we're going to take a look at this, and let's go ahead and kind of set this up the way that I did before. Let's go right to what's happening with the absolute value of this nth term expression. Well, that's simply going to lead us to eradicating the alternating component. We have 1 over n to the half, and hopefully we all remember that to be a divergent p-series. So, because of that, we have lost all possible hope to be absolutely convergent. Now we just test, are we going to be conditionally convergent? Well, to show conditional convergence, now you focus on, okay, what is really happening to this guy? What is his behavior? The only way to analyze an alternating series is, well, guess what? It's the alternating series test. So once again, the first step to the alternating series test is to take the limit as n approaches infinity of the non-alternating component, 1 over radical n. Well, once again, you've actually just completed that task. Now, although you may not have taken the limit over here, it's going to be a very quick process to take this limit. We find out that we do indeed get 0. The denominator grows really big. So far, the alternating series test is looking good. So we need to actually address option 2, or criteria 2. Now, criteria 2, if you guys were to look in your notes or perhaps recall an earlier video, it simply says that the nth plus 1 term must be greater than or equal to the nth term. I take that back. I apologize. I got those written in the opposite order. It will say just the opposite. The nth plus 1 term must be less than or equal to the nth term. It's kind of a way to say that your series is decreasing as we move term to term. Now, the best way to show this is to simply take a look at the denominator, this radical n, and just change out the n with an n plus 1 to get the nth plus 1 term. And then just sort of question, hey, is this a true statement? It turns out that the negative 1 to the n part can completely be left out because you would see that on both sides. Right? You could essentially cancel it away. And let's see what else we got to do here. One surefire way to do this is to cross multiply. Now, when you cross multiply across an inequality, you have to be very careful. Upper left times lower right, that result must stay on the left side to retain the inequality sign. And if you think just out loud, here's the square root of n less than or equal to n, the square root of n plus 1. Now remember, this is only going to hold for values of n that are 1 and greater, because that's what n does. It starts at 1, then goes to 2, etc., etc. And that certainly is true. So criteria 2 has been met as well as criteria 1, which means this series converges by the alternating series test. But if you recall, it diverged when we took the absolute value. So since we have sort of a conflict of terms here, that would mean that this guy is only conditionally convergent. Like I said, it is a little tricky. It's one of those things, like a lot of things in calculus and in math in general, the more you practice it, the more you'll get used to it. So I hope this helps, and we'll see you next